So this is where we were on Friday. I was just finishing up the Bohr model for electrons, and Bohr did a great job identifying that electrons are quantized, energy is quantized. We can only have certain allowable values. The electron can be on an energy level or the next one up after that, but it can never be in between. So there's allowable values for energy and there's not allowable values for energy. We all know, we've discussed it enough, the problem with Bohr was that he could only describe the electron energy in hydrogen. No other element would work using the Bohr equation or any other thing that the Bohr came up with. So that was a huge limitation, and we still didn't have a model that fit everything. Well, you don't have to write this down because I know before we talked about Bohr, I showed you a slide about Louis de Broglie in 1923. De Broglie came up with a relationship that said that any object that has mass that's moving, it's got to have some motion because it needs a velocity down there, the denominator with it. A moving object would have a corresponding wavelength. Well, it was that that Erwin Schrödinger used as a foundation when he came up with what we call the quantum mechanical model of electrons. And Schrödinger, using what de Broglie had come up with, that moving particles can have a wavelength and behave like waves, Schrödinger considered the electron to purely be waves. He did not consider an electron to be a particle. When it was moving, he just treated it as if it's a wave. So sometimes this is called the wave mechanical model, which is weird because we know electrons are particles. They do have mass. They interact with other things. But in this representation or description of electrons, they're just treated as if they're waves. So Schrödinger, he did things that we won't be able to understand in here. You've got a, well, this would be like a third-year chemistry course, probably third-year physics course. In chemistry, we call this study physical chemistry. So you'd like, often it's called P-Chem. You know, you take Orgo in your second year and then P-Chem in your third year. This is very complex. I'm going to use symbols that make it look like it's simple, like this. This is part of Schrödinger's basic description of electrons. He was assigning all electrons in an atom to a wave function. That wave, that's the Greek letter psi, and that represented a wave function. Now, even though it's just one symbol on here, what's behind that psi is a very big, complex mathematical model of what the electron is doing and how much energy it has. And this H, the H with a little hat on it, that's not some term that's multiplying by psi. It's actually what we call a mathematical operator that kind of gives a set of instructions to the Greek letter, the wave function psi. So this is math beyond what we're able to do. Drawing the pictures too?
Yep.
Sit there? Yeah. Well, some people stay, you know, everything that the teacher has on the board, you ought to copy down in your notes. So, just in case I have like a biographical picture on the test, you'll know who's who.
Identify the scientists.
Right.
I already know.
That'll be fun at the end of the year too. All the scientists you've seen pictures of, you can go back and see if you can tell who's who.
The only one I know is that guy.
Avogadro, yeah. Not having used the calculus and the math with this, I would have to go back and almost relearn it as if it was the first time for me. I mean, it is that complicated, and when you don't use it, it'll just leave your brain. Just like most of the French that I learned. I had a lot of French when I was in high school and college, and don't remember much French. Just because I haven't used it. Should have taken that annual trip to France, I guess. Then it would maybe stay with me. Okay, everybody good with that? So I want you to know that that when Schrodinger is treating electrons as if they're waves, he's not interested in saying exactly where an electron is. We won't be able to get that from the Schrodinger model. We won't know where the electron is. And there's a good reason that we shouldn't know where the electron is, because of this idea of the Heisenberg uncertainty principle. We can't know where an electron is.
So it's like a number.
These are all numbers. What do you see?
No, but it's just it's a constant. It doesn't change.
Yeah. We don't know.
So again, this is called the Heisenberg uncertainty principle. And keep in mind that an electron is really, really small and is moving super fast. Electrons are moving around the speed of light. I don't think they're going that fast, but they're going really, really quickly. So if we have a desire to see or track an electron, what do we have to do? We have to hit it with a photon of light that we hope will bounce back. And if you hit an electron with a photon of light, then you're going to throw off its motion. So that's what Heisenberg was saying. In fact, I have a definition of variables down here. The delta x is the uncertainty in its position, and the delta mv is the uncertainty in its momentum, or really its speed, because the m is constant. So Heisenberg was saying this: the uncertainty in the position and the uncertainty in the speed, when you multiply them together, it's greater than or equal to some constant number. H is constant, 4 is a constant, pi is a constant. And of course, Heisenberg was able to show this mathematically. Heisenberg was also working, trying to come up with an atomic model, a model for electrons, like Bohr did and like Schrodinger did. Heisenberg was very much into this, and so he used his method of calculating. Schrodinger was more about calculus and statistics, making a mathematical model of what electrons are doing. Heisenberg used matrix mechanics. He was using all these matrices. And do you remember doing matrices in Algebra 2, I think it is? Did you like doing matrices?
No.
I didn't like it at all, and I wouldn't. It just didn't really make sense. Why would you do all this work? It's so cumbersome. But that was the foundation of the math that Heisenberg used. He was a super smart guy. He just had that way of thinking, very organized, detailed. Ellen, do you have a question?
Yeah. For those like for just know the equation in the like what's that called? Guy called? Like,
Which one?
the one on the last slide.
The Schrodinger equation?
Yeah, Schrodinger. Like, do we have to know how to use the equation to do
No,
everything?
you don't. No. I'm making this very simple. In fact, it's so simple it doesn't mean anything right now. This does. It just says that we can't know the position and the velocity at the same time. Now here's Werner Heisenberg. Where do you think he's from?
Germany.
Oh, he's German again. Another German guy.
German guys are smart.
His name is Werner, but it starts with a W. I wish they could get that straight. The Germans, they just have trouble with that. But look at what a young guy he was. He was brilliant. And he would say that you can know maybe the position, but you won't know the velocity. You won't really know where an electron is going. The position is only in an instant, and then it's gone. So he's saying you can't track an electron, is what it's saying.
Here, you want to recite some German for us too?
Yeah, you lived in Germany for a little bit. 6 months.
Is that right, Garrett? You know, we could do some sauerkraut, maybe. You want to make some sauerkraut up from the pot at home?
After they beat them, we can bratwurst.
Yeah, some bratwurst and sauerkraut. We
Oh,
could,
it bumps in rooms.
yeah, that would be great.
For real.
So can we tell a difference in your drawings, Siddharth, between Schrodinger and Heisenberg?
I'm not sure.
Yeah, okay.
Oh yeah. Oh my God. Yes.
All right. Now, keeping this in mind, Schrodinger's model of where electrons are then, keep in mind, they're not going to be tracked, and we can't say an electron is precisely here compared to where the nucleus is. Schrodinger's model is going to give us clouds. We think the electron is going to be somewhere in the cloud. Not the cloud, the internet cloud, of course. But he's going to define these regions. He would have a cloud like this. And we think with a high probability, the electron would likely be found where the region is darkest. So that wave function, now we're going back to Schrodinger, the wave function really is not a physical quantity. It's not used to describe the electron because the wave function is a complex number. It's got that I term in it, the square root of -1.